Hello, everybody. Welcome to section 2.6, part 2. So before we talked about transformations of functions, in particular, we discussed translation and we also discussed reflection. And today we're going to talk about scaling of functions. Okay, so to start off, let's suppose we have, let's say, a positive number C. So we want it strictly greater than 0. And, some function f of x. All right, so let's look at our scaling guidelines here. So first off, if we multiply c on the outside of f of x like this is going to be vertical scaling. And the way vertical scaling works is that if c is bigger than 1, we're going to stretch. So it's going to be a vertical stretch by a factor of c. Okay. And then if, c is between 0 and 1, this is going to be a squeeze vertically by a factor of c. If c is just 1, you just get the function back, so nothing happens. That's why that one's strictly greater than 1 and the other one is strictly less than 1. So if c is bigger than 1, we get a stretch. If c is less than 1, we get a shrink. This makes sense. Okay. But now if we do f of cx, so if we do multiply everything by c inside the function parentheses, that's going to be a horizontal scaling. And the way horizontal scaling works is, honestly, it feels a little backwards. It feels a little counterintuitive, but let's just take a look at it. So if c is greater than 1, this is going to be a shrink horizontally by a factor of, and it's weird here too, it's by a factor of 1 over c, okay? And then if c is between 0 and 1, this is going to be a stretch horizontally by a factor of 1 over c. Okay, so the horizontal scaling looks a little funky, looks a little strange, but again, let's just do some examples, play around with it, and then let's see if we can kind of understand like why these are the rules for these sorts of scalings. So for our example, let's consider f of x, and let's do something simple again. Let's just do x squared minus 1. Okay, and so if we do x, let's graph this first with my usual 2 or 5 favorite points. So -2, -1, 0, 1, and 2. And if you plug these values into the function, you evaluate it, you're going to get 3, 0, -1, 0, 3. And so on a graph, that looks like something like this. Okay, so we have -2, 3 here, -1, 0, 0, -1, and on the other side the same. And then if we draw our parabola, it looks something like that. All right, so this is what our base function looks like. So let's scale it. So first off, let's try doing 2 on the outside. So this is going to be so this will be a vertical stretch by 2. Okay, and so if we actually look at the function when we multiply 2 on the outside, that's going to be 2 times what the function was, so x squared minus 1. And you could expand that out if you wanted to see it So let's do our table of values here. And so we're going to do 2 times f of x. And so this will be -2, -1, 0, 1, 2. And so if we evaluate, so at -2, we're going to have 2 times -2 squared minus 1. And that's going to come out to 6. And then 2 times -1 squared minus 1, that's going to come out to 0. 2 times 0 squared minus 1, that'll be -2. And then similarly, over here, it'll be 0, and this will be 6 again. So now if we graph this, like so, x here, y here, so plot our points. So -2 goes to 6, that's all the way up here. -1 goes to 0 again. 0 goes to -2, 0, and 6. And so now if we connect these dots like this, we see that it does look stretched. So if I overlay our original parabola over this, our original parabola looks something kind of like this. Okay, so it did stretch by a factor of 2. So that's good. Everything's making sense so far. Okay, let's move on to horizontal scaling. So let's say we wanted to do f, and then let's do 1/3 inside the parentheses. So this will be a horizontal stretch because it's less than 1. And it's going to be by a factor of, remember, it's 1 over c. So this is going to be 1 over 1/3, which if you do math is going to be 3. So this is going to be a horizontal stretch by a factor of 3. And if we look at this, when we plug it into the function, it'll be 1/3 x squared minus 1. All right, so let's do our table of values. F of 1/3 x. We have 2, -1, 0, 1, and 2. And let's see, we have 1/3 times -2, and that's all squared, minus 1. And if you do the math for that, I believe it comes out to -5/9. And then 1/3 times -1 squared minus 1, that's going to be -8/9. And then 1/3 times 0 squared minus 1, that's going to be -1. And then 1/3 times 1 squared minus 1, that'll be -8/9 again. And then lastly, we've got 1/3 times 2 squared minus 1. Again, that'll be -5/9. Okay. Now, if we do our graph down here, this x, y, let's plot our points. Make this one green. So we have -2, -5/9. So that's like, that's about right here. And then we've got -1, -8/9. That's almost -1. So that's going to be about right here. 0, -1. And then the same kind of thing on the other side right here. Like that. Okay. And then we'll connect our dots. Probably looks something like that. Okay, cool. So we can already see that even if I don't overlay our original parabola on this, you can already tell it's been just stretched out horizontally by a factor of 3, in fact. So that's good. All right. Here's the question, though. So there is a natural question that arises from looking at this. So question, does vertical squeeze equal a horizontal stretch? So if I were to, I don't know, say, stretch it horizontally by a factor of 2, is that the same thing as just squeezing it vertically by a factor of 2, right? Or a factor by 1/2. You might be tempted to say, yeah, of course, right? Because if you stretch it one way, it's the same thing as compressing it the other. Well, not necessarily. We're going to see why. So, well, consider. So we're working with f of x equal x squared minus 1. Let's just stick with that one. And so let's say we wanted to do a vertical squeeze. By a factor of 1/2. And we suppose that that's going to correspond to a horizontal stretch by a factor of 2. But note, because we're going to need c equal to 1/2, because then we get factor of 1 over 1/2, which is going to be 2. So we're going to need c to be 1/2 for this side. So now let's go ahead and just look at it algebraically. So let's look at 1/2 f of x. And if we do that explicitly, that's going to be x squared minus 1 all times 1/2. And we can expand it out just so it's going to be 1/2 x squared minus 1/2. Over here, if we do our horizontal stretch by 2, that could be 1/2 inside the parentheses. And if we plug that in, we'll get 1/2 x all squared minus 1. And then if you distribute that squared, it's going to be 1/4 x squared minus 1. And already you could tell by looking at these formulas that these right here are not the same. And in fact, if we graph these, if we look at a graph of them, put some tick marks on here. So our original f of x looks something like this. And I drew these out a little bit beforehand. If we do the vertical squeeze by 1/2, that's going to look like this kind of. So this is 1/2 f of x. And then if we look at the horizontal stretch, that's going to look like this. So this was f of 1/2 x. All right, yeah, so just looking at these pictures, even though the parabolas look like they're about the same shape, they're not the same. They don't lie over each other, right? And that makes sense because their equations aren't the same either. Okay, so in fact, no, not the same. So just be careful when dealing with scaling like this, because depending on what kind of scaling you're doing, you can't really interchange it with other kinds. Okay, so one last note before we wrap up today. So we're going to do a note on odd and even functions. But what do I mean by an odd and an even function? Well, okay, so f of x, some function, we're going to say is even if f of negative x equals f of x for all x in the domain. And then we're going to say f of x is odd if f of negative x equals negative f of x for all x in domain. Okay. So this is what odd and even functions mean. Just looking at the definitions doesn't tell you a whole lot about why this is important. And in fact, not all functions fall into these categories, right? There are definitely functions that aren't odd, and they also are not even, right? So let's see some examples. So if I do f of x equals x squared, that is going to be even. And you can see that because every time you plug in like a negative number, the x squared is going to be negative times negative, which will shoot it to a positive number. So it's an even function. And then if we look at like g of x equals x to the fifth, that's an example of an odd function. And you can kind of check that on your own. Okay, why are we talking about this? So why do we care? The answer is symmetry. Symmetry makes some transformations easier to deal with. So in particular, even functions are symmetric about the y-axis, and odd functions are symmetric about the origin. So if we look at that in pictures, so if I just sketch a quick graph here, maybe if I do something like wiggle, maybe it dips down. To make this an odd function, it's going to have to do the exact same thing on the other side. So this is an example of an odd function. And then an even function would look more like this. X, Y, little curve because of the origin, and curve up here. And so if you look at like the first quadrant, so where everything is positive up here, if you look at that quadrant and you imagine you like rotate it about the origin, then it'll end up here. And so that's what it means to be symmetric about the origin. So this is an even function. Oh my gosh, I got them mixed up. Even though I have my notes right in front of me. This one is even, my bad. You probably caught that before I did, of course. Oh boy. But sorry, so the blue is an even function because if you look at it, everywhere that there's negative f of x, or sorry, everywhere that's f of negative x, that's going to be f of x, right? So if you imagine like this is 2, you look up here, it's this point. And if you look at like -2, it goes up here and it hits like this point here. They're at the same level. So that's an even function. And this one over here is odd. There we go. That's better. All right. And even and odd functions won't come into play a lot in this course, but I wanted to mention them to you because if you take any other math courses beyond this, they will probably use facts about odd functions and even functions. So they're good to just kind of see them and kind of know what those words mean a little bit, just so you can use these concepts later. All right. So in the video, we discussed mostly scaling and the trickiness and pitfalls therein. But just keep working on it, keep practicing those transformations, work on your homework, and if you have any questions, of course, I hope to see you in office hours.